we're going to be talking about what's called the normal model. So this is a very important concept in statistics. We're going to use what's called the normal model to answer a few questions. Let's assume the cholesterol levels of an adult can be described by a normal model with a mean of 206 milligrams per deciliters and a standard deviation of 18. So we're asked to complete parts A through E. So part A, draw and label the normal model. Part B, what percent of adults do you expect to have cholesterol over 225 milligrams per deciliter? Part C, what percent of adults do you expect to have cholesterol levels between 180 and 190 milligrams per deciliter? Part D, estimate the interquartile range of cholesterol levels. And Part E, above what value are the highest 15% of adults' cholesterol levels? Alright, so let's go ahead and take a look, and I'll be referring back to these questions and scrolling up. The first question says, draw and label the normal model. So, the normal model will be as shown. We have our curve, and within this curve, we have the 68%. So 68% of the values fall within one standard deviation. If we relate this normal model to our example talks about the mean cholesterol being 206 milligrams per deciliter. So 206 will be right there in the center. Between one standard deviation, and they gave the standard deviations in the beginning as 18. So 206 plus the 18 makes 224. 206 minus 18 gives us 188. So this means that 68% of the values fall within one standard deviation. Well, they fall within 188 and 224 milligrams per deciliter as far as their cholesterol. Alright, next we have two standard deviations. So two standard deviations. So with two standard deviations, we say that 95% of the values fall within two standard deviations of the mean. So if we take 206 and we're going to add two standard deviations, so we have 2 times the 18 that was given as the standard deviation. So that'll be 206 plus that value should give us 242. Right? And we want to do the same thing with 206 and then subtract 2 times the 18. So doing that calculation, we get 170. So we can say that 95% of the values fall within two standard deviations. That's between 170 and 242. Alright. And then we have three standard deviations. So this will be 99.7%. So 99.7% of the values fall within three standard deviations. And going above, we'll say 206 and add that to 3 times the 18. 206 added to 3 times the 18 will get us 260. And then to the left, 206 minus 3 times the 18 will get us 152. So 99.7% of the values fall within three standard deviations, which is, for our example, between 152 and 260 milligrams per deciliter. So this is the normal model according or specifically relating to our example. Our next question: what percent of adults do you expect to have cholesterol over 225 milligrams per deciliter? So the next thing we should do is make a picture so that we can see this a little bit better. So we're going to make a picture of the normal model as it relates to what this question is asking. So as you recall, our 206 was the mean cholesterol level. We had one standard deviation was 224 to the right and 188 to the left. However, in question is cholesterol levels over 225. Over 225. So if this was 224, 225 will be right next to it. So we're actually looking for this shaded area, right? We're trying to find that area under the curve. And then that'll help us figure out what percent of adults will have cholesterol over. And remembering that the value that we found for the z-score was 1.06, we're going to go to the table. So on the left hand side we see the z-scores from the whole number and the tenths place. At the very top we see a tenths place and a hundredths place. So we're going to match those up. But first we have to get out of the negative because our z-score was 1.06. So I scroll down and I get to 1.0, and then I'll go across to 0.06, right? The 1.0 and the 06. The 1.0 and the 06. Where they match up is way over here, and it says 0.8554. 0.8554. So from the table we have a value of 0.8554 given that z-score of 1.6. So we get this from the table. So understand that when we use the table, the values that are given give us the areas to the left of whatever your value is, such as our 225. So this 0.8554 is everything here in this white space. However, remember, we're looking for this shaded region. So since the area under the curve is 1, we would just take 1 minus 0.8554. 1 minus 0.8554 gets us 0.1446. So what does this tell us? It tells us that about 14.46% is the percent of adults expected to have cholesterol levels over 225 milligrams per deciliter. The table was a nice way to work through the problem. However, we can also use technology. The technology that I'll choose here is StatCrunch. So let's go to the Stat tab, Calculators, and then just go down to Normal. So here's our normal calculator. We can either choose the standard, which gives us values that are less than our value that's in question, or we can choose between to get the area in between two values that are in question. Again, our question wanted us to get an area or percentage that was greater than, right? Greater than. As you see, we can't do that on this calculator. However, there are probably many others that can. So what I'm going to do is just use the standard of less than, and I'm going to type in the information that was given. The mean was 206. The standard deviation given was 18, and we're looking for, in this case, we'll say less than 225. So then we'll go ahead and compute, and again we'll get 0.8544. which is the exact same we got when we used the table. So I would get this value, subtract it from 1, and still get the value of 0.1446, which is 14.46%. The next question states, what percent of adults do you expect to have cholesterol levels between 180 and 190 milligrams per deciliter? Alright, so this is the in-between problem that I was mentioning when I looked at the stat crunch. So we're looking for the area in between those two values, 180 and 190. So the first thing I'm going to do is make a quick picture, right? I always like to draw the picture to show how it looks. All right, so again, if the mean of 206 is right there, and if we can think back to where one standard deviation was, right, the 188 and the 224 are at those tick marks, and two standard deviations, 170 and 242 were at these tick marks, then 180 to 190, right? 180 to 190. So 180 to 190 is probably somewhere between these two lines, this shaded area there, right? So that's between 180 and 190. All right, so in drawing that helps me out. That helps me understand the situation better. So what I'm going to do is go ahead and find the z-score for both of these values. So the z-score, y minus mu, again, over sigma, for the first value. So the first value is 180 minus mu, and remember mu was given at the very beginning. It's 206. It's right there as well. And sigma, the standard deviation of 18, was given as well. Well, you go ahead and crunch these numbers and you get a z-score of negative 1.44. So I do the same process, find the z-score for the other value. The other value was 190. Remember, we're doing it between 180 and 190. So 190 minus the mean of 206 divided by 18. Crunch these numbers and we get a negative 0.89. Negative 0.89. So we're going to try to find the area, right, where the z-score is between negative 1.44 and negative 0.89. So our calculated z-scores were negative 1.44 and negative 0.89. So let's look for them on the table. So negative 1.44. Negative 1.4 is right here, so we'll have to slide over to the 0.04 column, and we get 0.0749. 0.0749. So we need to write that down. And then our other z-score was negative 0.89. So we go to negative 0.8, and then we go all the way across to 0.09's column, and then we see the value of 0.1867, and we write that down as well. So going back, we're going to go ahead and perform our calculation. So we said we've gotten 0.0749 and 0.1867, right? So understanding that we're trying to find the area in between those two, we can subtract 0.079 from the 0.1867. Doing so, we get 0.1118. This is the area in between those two values. So if we go ahead and change it to a percentage, we change it to 11.18%. All right, and 11.18% is the percentage of adults expected to have cholesterol levels between 180 and 190 milligrams per deciliter. Our next question wants us to estimate the interquartile range of the cholesterol levels. So the interquartile range will be equal to the difference between the lower and upper quartiles. Let's take a look. So through my picture, I can see that if here we have the 25th percentile, and in drawing another one, this will be the 75th percentile. So basically, if we take the difference between these two shaded regions, we'll get what's in between, which will be the difference between the lower and upper quartiles. So the first thing we need to do is go ahead and use some technology, and we're gonna find the area, which is 0.25, and the area, which is 0.75. So in finding the z-scores for those areas, that'll help us on our route to solve this problem. Let's take a look. So what we want to do next is use the technology to our advantage. So we're going to find the probability where x is less than z. So here I'll plug in a 0.25, hit calculate, and the calculator gets us a negative 0.674. Negative 0.674. Now let's do the same thing for 0.75. So the calculator gets us a positive 0.674. A positive 0.674. So again, we get a negative 0.674 and a positive 0.674. So these will be our z-scores, our corresponding z-scores. Alright, so now we're going to convert these z-scores into their original units. So remember, the formula is z equals y minus y bar over sigma. So we're going to plug in negative 0.674 for z, which is equal to y is what we're trying to find, their original units, minus 206, which was given, over 18. I'll do the same thing for this side, y minus y bar over sigma. So my z-score is 0.674, equaling to y, which is what we're trying to solve for, minus y bar is 206 over 18. Just performing some algebra on both of these, we can eventually get that y is equal to 194, and here y is equal to 218. So the IQR for us is going to be the 218 minus 194. If you recall, it's that Q3 minus Q1 for us is that 0.75 minus the 0.25. So here we get 218 minus 194 is 24 milligrams per deciliter. Last question. Above what value are the highest 15% of adults' cholesterol levels? The highest 15%. Where would that be? If we drew a line right here and called this 85%, this shaded region right here that I'm filling in, that shaded region is the 15% that's in question, the highest 15%. So we're just going to go straight to the technology. The technology is going to help us to find the z-score that we need to perform the calculations that corresponds to this area that we're looking for. Let's take a look. We go to the technology and I'll input 0.15 and enter. And as you can see, as I input the 0.15, the z-score calculates to 1.036. 1.036. 1.036. Alright, so now we can use this information to go ahead and calculate the original units. So the z-score formula is y minus y bar, or we can say y minus mu over sigma. So here we can say 1.036 is equal to y minus, the mean was 206, the standard deviation was 18. Now it's just a simple algebra problem. We would go ahead and multiply both sides by 18, which would get rid of the fraction for us, and then go ahead and solve for y. So here, solving for y. Solving for y would get us y is equal to 225. So 225 milligrams per deciliter. The highest 15% of adults' cholesterol levels are above 225 milligrams per deciliter.